So we've talked about galaxies individually, and the one thing that maybe we realized almost immediately is that galaxies are quite close to each other. So the idea of galaxies interacting with each other is much more important than for stars. And in fact, that is what drives a lot of galaxy evolution. So galaxies, unlike stars, stars for the most part are isolated from other stars. You start the star out, its mass doesn't change with time. It just sits there until it runs out of fuel. Galaxies, on the other hand, they'll run into another galaxy. They'll get fed with more gas as they're growing. So for the most part, they aren't a closed system. There are some galaxies that do behave like that, like they started near the beginning of the universe and nothing has changed with them since. All the stars in that galaxy are gradually dying, and that would be sort of passive galaxy evolution, but there's a lot more going on in galaxies. So first we'll talk about how galaxies are distributed in space, and more evidence for dark matter, and then think about what happens when galaxies run into each other. So the first thing is, like with stars, galaxies like to hang out with each other, and even maybe more so than stars. So we think there are lots of stars who are in binaries, but in fact, most galaxies are in little groups with other galaxies, right? They aren't isolated. So this is the Ursa Major cloud, not the greatest picture, or at least it doesn't look so great up there. It looks better here. And the Virgo cluster, which we've been talking about a lot with that galaxy of M87, which I believe is just this guy here in the middle, although that looks a little bit smushed, but I think this is M87. I think, unless that is. He's more circular. I bet this is M87, is the galaxy that we talked about a lot. It's over there. So typically galaxies exist in groups. So if we think about our galaxy, it is in a group that has maybe 2 or 4 biggish galaxies and lots of small ones. And the difference, like I'm saying, it's 2 or 4, it's what you define as biggish. But then you can have a cluster like the Virgo cluster here on the right, which has dozens or 100 big galaxies, meaning galaxies the size of ours, or maybe somewhere between like a half or a tenth of ours and bigger. We can call that a biggish galaxy. Okay? And they go up to ones which have thousands of galaxies. So the Virgo cluster, it just happens to be nearby. It isn't a big cluster of galaxies. They're ones that are tens of times larger. So galaxies are typically in either groups. Let's say about half of the galaxies are in groups, which means less than 10 big galaxies. And then the other half are in clusters, which are ones that have hundreds to thousands of galaxies. So here's a picture sort of in 3 dimensions showing what's going on in our local group of galaxies. And you drew a few of these objects in your picture there. So you have our Milky Way galaxy is up at the top with a whole bunch of other galaxies that orbit the Milky Way galaxy. They did the color coding maybe the opposite I would have done. So they made spirals yellow, which is probably okay. I would have made irregulars blue because they look blue, but here ellipticals are blue. Maybe I'll try to change that. That might be a little bit of work. But if you look at our galaxy, they've classified the small and large Magellanic Cloud also as spiral galaxies, but you can see that's a bit of imagination for those guys. But they're big galaxies, or the among the bigger galaxies that are orbiting our galaxy. And then there's a whole bunch of small elliptical galaxies that are orbiting our galaxy as well, and those have, Carina, Sculptor, Fornax, etc. Okay? In our local group, there is another large galaxy, which is the Andromeda Galaxy, which is like sitting right here. And it has a whole bunch of small elliptical galaxies orbiting it, and their names are there. And when you see a picture of Andromeda, generally you see two elliptical galaxies are sitting right in the same picture whenever you see Andromeda, and those are NGC 205 and M32, right? And those two are two small elliptical galaxies orbiting Andromeda, and there's a relatively big spiral galaxy called M33 that's quite pretty, that also orbits Andromeda. But this is maybe a prototypical group of galaxies that we have. Maybe, depending on your count, you have 2 big galaxies or maybe 4 big galaxies if you count M33 and the Large Magellanic Cloud. Now, you can ask the question, like, where are the black holes? Yes?
These 2 big ones orbit each other.
Yeah, well, like, they've not gone past each other yet, right? So they've not, since the beginning of time, they've never done this. What they're going to do is they're going to slam into each other in, 3-ish billion years. And I'll have pictures of that in a little bit, what it'll look like. So our Milky Way has a black hole in its middle. We talked about it. Andromeda maybe has 2. We think it has at least 1. And of all these elliptical galaxies that we talk about, M32, is an elliptical galaxy, also has a black hole. So in a certain sense, M32 is like the smallest elliptical galaxy that we know of, or whatever in quotes, that has a black hole. So that's the end of that long sequence of mass versus black hole. And its mass of its black hole in M32 is comparable to that of the Milky Way. So that's a picture of our local group. So most of the stars in our local group are in the big spirals, our galaxy and M31. So if we think of ourselves as living around an average star, it makes sense that we are sitting in a big spiral galaxy. So if we look out in the universe, about half of the galaxies are in the groups, and essentially about half of the stars in the universe end up in these spiral galaxies, right? And that are in groups. If we actually count the galaxies, most of the galaxies in the local group are little guys, like this guy. This is NGC 205, and this is M32, Messier 32. So most of the galaxies, if we were to count, are these little galaxies. So there are lots more little galaxies in big galaxies, but there's lots more stars in the big galaxies than in the little galaxies when we add them all up. So if you think about all of these little galaxies out there, and they're very close to the big galaxies, you would guess occasionally they run into each other. And not really occasionally, all the time, effectively, big galaxies are eating up little galaxies. And we see here, if we look towards the center of our galaxy, and we count stars, we see, like in this region here above the bulge, there's an excess of red giant stars at a particular distance from us. And if you plot out that excess, that's what it looks like in red. And in fact, they're all moving together in the same direction. And what that is another galaxy called the Sagittarius dwarf spheroidal, it doesn't look very spheroidal, does it? It's kind of, and that's because it's right now being shredded by the gravity of our galaxy. It's being eaten up by our galaxy right now. So this is a small galaxy being consumed by our Milky Way, and we can just, it's happening now, which sort of makes you think that it's a quite common occurrence, right? So this is Sagittarius, so that's on the other side. So the evidence that we have for this is we can look at the dwarf galaxies that are orbiting our galaxy, including Sagittarius, and we can follow, if there's a galaxy, a dwarf galaxy somewhere, we notice across the sky is a stream of stars that have been shredded from that galaxy over the course of time. So every time this guy kind of comes close to the center of our galaxy, it loses a bunch of stars, but those stars keep going in more or less the same orbit, and they trace what's called a stream across the sky. And we see lots of streams. So for example, the large and the small Magellanic Cloud are connected by a stream of stars and gas that also extends around. So the fact that these galaxies are living so close to us, to the Milky Way, the gravity of the Milky Way gradually over time shreds those galaxies, and then those stars form. If you think about these streams, eventually they get mixed up and they form all the stars of our halo of our galaxy, and the stars in that little clump, they will get added to the disk and bulge of our galaxy. So here's a picture of, from the point of view of Earth, right? So we're standing on Earth, and in frame one, we see from our point of view the Milky Way, right, which is over here. And in the current picture of the Milky Way and Andromeda, the Milky Way is like this, and Andromeda is a little galaxy down below the Milky Way. So what's happened since then, since from today till that picture, number one is the Andromeda is coming straight at us, more or less, or we're going straight at Andromeda, depending on how you think about it. So here now, maybe 3 billion years from now, Andromeda is pretty darn close. It'll take up a large fraction of the northern sky. It would be pretty amazing, right? So Andromeda's like up in it's in the constellation of Andromeda, for what it's worth. But it would appear much, much bigger in the sky, and effectively we would see two Milky Ways, because the Andromeda galaxy would be so bright and dominating that picture. So here it is. It's not yet. It just appears behind the disk. It's not yet collided yet. Then we go to stage two. The two galaxies now are shredding each other up, and we're in one of them. So this is from our point of view. We see now the disk of our galaxy is pretty hopeless. It doesn't look much like a disk. The gravitational interaction of these two galaxies incites tons of star formation, like we've seen in in that Whirlpool galaxy. You see lots of star formation that gets incited by the tides of that little galaxy. And with time, it just gets messier, more star formation. By point 4, what we're seeing here now is really the centers of the two galaxies merging. So what's going to happen is the two galaxies come close to each other. Essentially, the disks of both galaxies get shredded. We live in the disk of our galaxy. So now we're just kind of floating out aimlessly, not within the disk anymore, because there is no longer a disk. And then over here, these are the two central regions of the galaxy. The two bits come in and they will orbit like maybe one more time right in the center. And that's what we see in number 4. Number 5, all that's left that's distinct is the bulges of I don't know which is which in number 5. One is Andromeda's bulge, and one is the Milky Way's bulge. And then eventually it all settles down to number 6, and that's what the night sky will look like about 5 billion years from now, or a little bit less. Except it'll be a lot warmer on Earth because the sun will be a lot warmer, but that's a whole other thing. So over there, number 6, that's what the sky would look like if you lived in the middle of an elliptical or on the outskirts of an elliptical galaxy. So that's the ultimate fate of our local group, will be these two big galaxies merging. There'll be a single big elliptical galaxy with maybe a spiral or two and a couple other galaxies orbiting around us. So I don't know. I don't know if that's a good thing or not. That's kind of whatever. Now, you could ask questions like, is this bad for us? Not so bad, except during this stage 2 and 3, there's going to be lots of supernova going on near us, maybe. That could be bad for us, because if one's especially close to us, it could give us a lot of radiation. It could be unpleasant. And the other bad thing that could happen is, in these stages 5, 6, you could reignite the AGN in the center of our galaxy. And since it's not like in a disk galaxy, like we're here, our AGN in the middle of our galaxy probably has operated in the recent past, but it's generally the jet will point vertically out of the disk, not towards us. If we're really unlucky, we could get the AGN jet pointing at us in number 6, which would be unpleasant, but probably the main effect of that would reduce the size of the solar, whatever, how big the solar system is. So all these charged particles would get blocked by the solar wind, hopefully. We have other things to worry about, though. Yes?
How long from 1 to 6?
About 1 billion years, maybe a half, maybe a few 100 million. Okay? Because I don't know how far away it is here. Like here, they're really all messy, right? So from here to here, actually doesn't take that long for it to settle down into something like an elliptical. So if we look at the two nearby clusters of galaxies in more detail, we have the Virgo cluster on the left and the Coma cluster on the right. So Coma is the nearest big cluster of galaxies, and you can see, there's so many galaxies in there. Like all of these little guys here are galaxies in the Coma cluster. That's a star. That's a star. So someone asked me, why do the stars, so these spikes, in an image, the spikes come from an artifact in the telescope. Like that, depending on the telescope, it can be how the secondary mirror is held up. And you don't see spikes in the galaxies because they're inherently fuzzy, and that averages out those spikes. So just like if you think about looking at the stars from the surface of the Earth, you go, oh, stars twinkle and planets don't, because planets really are kind of big. If you look at an image of the sky, the stars have spikes and the galaxies don't, generally, for the same reason, because the stars are inherently small. A planet wouldn't have spikes either, but a planet would look like that in the picture. It would be obviously something like that. So if we look at these guys, if we look at Coma, it has a lot more galaxies in about the same volume. I didn't really tell you about the size. So the size of our local group loosely is something like 3 million light years across, or 1 million parsecs, a megaparsec. And as we go to bigger groups of galaxies and clusters, basically you're packing the same, more galaxies in the same volume. So that idea of 1 million parsecs is the characteristic size of groups of galaxies. Okay? So it's not that Coma has more galaxies packed into the same volume as Virgo, and Virgo has more galaxies in the same volume than our local group. So the size stays the same. So if we wanted to measure, learn more about these clusters of galaxies, you have a huge amount of mass in a volume, and this mass, as light passes it, it gets bent. So we can actually look at galaxies behind the cluster, and in fact, it magnifies them. So this picture here identifies the same galaxy, in fact. So this is one galaxy, and we see different images of it. Here, this big stretchy image, here, and this is another image of it from in the center of the cluster. And you can see here there's this streak. This is probably a different object. But the objects that happen to line up, if you imagine the cluster's here and we're here, and if there's some object directly behind the cluster, from our point of view, its light gets stretched out and it goes around the cluster and bends like this. So it can form a ring around the cluster. And here we're seeing parts of that ring from the same galaxy. So by looking at these different galaxies, first of all, we get a nice close-up view of a much more distant galaxy. It's actually been magnified by a huge amount, but it's also been distorted, which makes life a little hard. But we can learn about those distant galaxies that way. But by understanding how much they're magnified and distorted, we can measure the mass and the structure of this cluster. And in fact, once again, we find that the mass is dominated not by the light, but by some dark matter that we don't know what it is. And another cute thing is that if you imagine that there was a supernova that went off here in this galaxy, what we would find is we would notice the supernova would go off here and then sometimes later go off in this image and later still in that image. This is actually two images of the same. They're sort of almost connected. So if we measure, if we see some change in one image, it'll happen at a different time in all the other images a number of years later, because it takes the light a different amount of time to go around each of these paths. And once we know that, we can measure the size of everything. And that tells us how big the universe is, which is effectively our Hubble constant. Okay. So here's just a picture of how it goes. If we have an observer from Earth, we could have some object, let's say a quasar, that sits behind the galaxy. This shows us getting two images from the quasar. We'll actually get a third image that runs straight through the middle. And that's what we saw in this picture, that you get all of these, 4, plus a fifth one in the middle. That's not so magnified. In fact, it's much smaller than those. So you'll get generally an odd number of images. So here, depending on whether the light went on one side of the galaxy or down at the bottom, we get an image either to the left or to the right of the galaxy. But the amount of time it takes to go one way versus the other is different. So we can measure, if we can measure that difference in time, that tells us how big that whole picture is in meters. And then if we know the redshift of the quasar, that tells us the Hubble constant, because we now measure the distance to the quasar directly, believe it or not. That's okay. So here's a pretty picture of gravitational lensing around a galaxy like the picture before. So here we see, again, we're looking in a cluster, and there's lots and lots of gravitational lensing. Like you can see them as these arcs. Your eye is very good at picking them out. You see this, right? Or this, down here. You see these lines. Those aren't really galaxies that are so stretched out. that is just due to the gravity of this cluster will magnify objects, and the objects that are magnified also get very distorted in that direction. And if you were to think about where all those circles go, those circles circle where the mass is, effectively. But now if we look at this little galaxy in the middle, it happens to have a quasar right behind it. And we see 4 images of that quasar, right? And they're indicated by the arrow. And they're more or less symmetric around the center of the galaxy, right? So the reason why this works, why this becomes so important, is that, like, the sky is absolutely full of galaxies. Like, if I look at a part of the sky, most of the sky is full of the light of, not most, but a large fraction of the sky is full of the light of galaxies. Right? If you look at stars and zoom in, you'll just see little dots, and they'll still be very far apart. Remember, the galaxies are much closer together with respect to their size, so that means that they collide with each other. That also means that you get effects like this gravitational lensing being very important, because if I look in one direction of sky, there's a good chance that there's some object between us and it. So we see these effects, right? So here's one where we can put a whole bunch of things together. So if we think about these clusters of galaxies, they have a lot of stars, and these stars are in the galaxies. They have another component that I didn't talk about yet, and that is gas. So there's the gas that's left over from making the stars. It's also, as the stars die, they have supernova. And also, if they just die like the sun, they eject the gas from them. And that gas, a large fraction of that, ends up sitting in between the galaxies of the cluster. In fact, most of the mass in a galaxy cluster is in that gas that sits between the galaxies, the intra-cluster medium. Now, this gas is heated up by the motion of the galaxies up to millions of degrees. So it glows in the X-rays, in fact. So this picture in red shows the glow of the X-rays. Now, what's funny about this cluster is it's called the bullet cluster. But really what it is there's one cluster of galaxies over here and another cluster of galaxies over here, right? And you can see there's lots of galaxies here, and not so much in the middle. So you have 2 clusters of galaxies. Now what's happened, though, is the gas, which is highlighted in red, is not where the galaxies are anymore. The gas is stuck in between. So what we think has happened here, and the arrows kind of help your imagination, is you had 2 clusters of galaxies with gas, and they pass through each other. Okay? Now, the galaxies themselves, they don't run into each other. I mean, I know they're close together, but they can fly through. There's space in between them for the 2 clusters to go through. But the gas just runs into itself in the middle, and it gets left in the middle, is what you see in the picture. So the gas has been left in the middle between these 2 clusters. So this is the X-rays. Now, the blue is something else entirely. So the blue is, by looking at the galaxies in the background, we can figure out where the mass is. Where is the mass in this picture? And that's given in blue. So the most of the mass is, in fact, still sitting where the galaxies are. So each of those galaxies has its dark matter halo, and that dark matter, when it went through, it just kept going. So the dark matter just propagates through, just like the galaxies did. And this kind of demonstrates that dark matter has to be something, it can't just be, let's adjust the laws of gravity and pretend there's no dark matter. Because most of the mass of normal material in this picture is where the red is. Most of the mass in this picture of normal material, like the stuff in the periodic table of hydrogen and blah, 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 is where the red is. but the gravity is centered where the blue is. So the gravity is coming from some other component, not what we call baryonic or normal matter. So here, where we left off was this picture of the bullet cluster, which, the things to take out of it is it really tells you something about the qualitative about dark matter, in that, first of all, like whatever dominates the mass in this picture, it doesn't run into itself. It doesn't interact very strongly with other material. So the bulk of the mass that we measure is here in the blue, and it sits on the galaxies, where if we were to count in this picture, where are most of the atoms? That's normal stuff. It's where the red is. So it's saying that gravity, in fact, isn't associated in this picture with atoms, with normal matter. It's coming from some other source, which is we call it dark matter. But we don't need, this is just reviewing, so this is looking at the, that's all on. We don't really need that. If we look at the rotation curves of spiral galaxies, we see that the rotational velocity can actually increase as you get further and further out in the galaxy, whereas the material is not there anymore, or at least the normal matter isn't there. There was actually a recent thing in the news, which was kind of interesting and weird, and at first I was like, no, that couldn't be true, but essentially, that's how astronomy works. Often things, that couldn't be true. But they measured far out at the edge of where you could last measure the motion of gas. So that's the edge of the galaxy, but there could be more dark stuff beyond. And they found that all of the spiral galaxies, like that last point on the right, they go around once every billion years. Which is weird, and I don't know what it means, but it's in the news, like in the last few days, if you're curious about it. I think it was, I don't know. I think it was on Tuesday, perhaps, that it came out. So it's kind of a weird thing, but there you go. So we see this evidence for the dark halos as we go further and further out. So the biggest galaxies, when you add in the dark matter, are a galaxy like M87, let's say, which are about 1 trillion solar masses in their total mass. So the mass of 10 to the 12 suns. So these are the largest galaxies in the universe. They are typically these big elliptical galaxies in the middle of a cluster. Now, if we look bigger, on bigger scales, this is looking at a cluster of galaxies, and again, that blue color that's plotted on top is the mass that we measure for this cluster of galaxies, where it lies, and we measure it from the gravitational lensing. And you guys should be able to see, at least when I look at it, I see that there's lots of gravitational lensing by this cluster. How can I see it? What do I see in that picture, other than the blue light? The blue light is measured from that. But if you look, at least for me, I see lots of these little things, these little arcs, like here's one, up here's one, the really long one. And these are things that your eye is actually pretty good, and your brain is pretty good at picking out. But for me, I see lots of things like going in a circle. So this is a really great picture of showing. Do people see that, or is that just my imagination? Or I've looked at these pictures a lot, so I can pick it out. So basically what they do is they look for that pattern statistically, this sort of things going in a circle, and that tells you where the mass is And then that's plotted there in the purple on top of those images of the actual galaxies. Now, if we look at this, we come to the conclusion that dark matter comprises about 90% of the matter in the universe. And what do we mean by matter? That means the stuff, whether or not we understand what it is, that stuff is the stuff that gravitates other stuff in a normal way, right? So dark matter is a little weird in that we can't see it, but its gravity is like normal gravity, right? So a bit of dark matter attracts another bit of dark matter. We'll find that there's weirder stuff in the universe, don't you worry. But the dark matter at least has normal gravity. What makes us up and what we're familiar with, the atoms, are only 10% of the normal of the matter in the universe, okay? So if we look into a cluster of galaxies, like we were talking about even in our local group, but in a cluster it's even worse, the distance between galaxies is quite small compared to their size. So the galaxies are always almost running into each other. So inside a cluster, if you remember, the size of a cluster is similar to the size of our local group. It's just you've packed, instead of order 10 galaxies, you pack 1,000 galaxies in there. So the galaxies are on average 10 times closer to each other, so they interact more. So we think, well, these are different pictures of galaxies in the process of interacting. So galaxies actually collide with galaxies a lot in the universe, and these pictures are of galaxies of about the same size colliding with each other. So in the course of the history of a galaxy like our own, since there's lots more small galaxies than big galaxies, collisions between small ones and big ones are much more common than between big ones and big ones. But even for our galaxy, we think most big galaxies have been involved with a good-sized collision, and most big galaxies right now are eating little galaxies right as we speak. That's how common it is. And we talked about it earlier, how our galaxy is eating this little dwarf spheroidal called Sagittarius, but the rest, that was just the appetizer, the amuse-bouche. There's lots more galaxies waiting to be eaten by our galaxy as time goes on. The Large and Small Magellanic Clouds, the second closest galaxy to ours is in fact the Large Magellanic Cloud, and it will be eaten before too long. And then we'll be involved with a collision like these with Andromeda in a few billion years, as we talked about earlier. So this is a great picture of a nearby galaxy called the Antennae, which is a pair of spiral galaxies that are in the process of merging together. So it gives an idea of what is in store for our future. So those pictures that I showed you of Andromeda colliding with us are effectively inspired by what we see here in the Antennae galaxy, right? So these were spiral galaxies. That's what's left of them right now. So the reason I know that they were spiral galaxies, you may ask, because it's like so ugly now. How do I know that they were spiral galaxies before? What do you think? What if they were two elliptical galaxies? They definitely merged together too, but how would the picture look different? It would be ugly, it would be uglier than this picture, I'll tell you. It would be messy like this picture, but there's something about this picture that tells me that I put spiral galaxies together.
The area of dust and active star formation?
Exactly. Where it's red and where I see dust tells me that the galaxies that came together here had a lot of gas. And the reason I see star formation, how I know there's star formation is the red. that red color is young stars forming, because what they do is when they're forming, they ionize the gas around them, and that ionized gas emits that red color there that we've talked about, which is just a hydrogen atom going from its third level, dropping to its second. So we know just from the colors that this is, they were two spiral galaxies. I mean, we could look closer and we could imagine there's some vestiges of the spiral structure, but the key thing is that there was gas in here. And in the future, this antennae will look like an elliptical galaxy, more or less. Maybe not so pretty. So we have, if we look in smaller groups, we have this interesting thing that happens, right? So if you imagine a cluster of galaxies, there's lots of galaxies in there, and you would say, oh, these two galaxies, it's quite likely that they'll go past each other close because the density of galaxies is higher, right? And that makes sense. But in a cluster of galaxies, the two galaxies, they'll come past each other, but they'll go past each other quite quickly. So they have very little time to interact with each other. And unless they really have a head-on collision, they won't do that much damage to each other. So in a cluster of galaxies, although the density is really high, the galaxies tend to just whiz past each other. In our local group, what happens is, there's this fun thing that galaxies can actually pass through each other in a cluster, which we can talk about in a little bit. But in a group, what happens is the galaxies, as they pass each other at about the same rate as each galaxy is spinning. So why is that important? So when it comes close, this galaxy starts pulling on stars in this galaxy, but this galaxy is also rotating at the same rate. So this galaxy is actually upsetting these stars, but it's always upsetting the same stars as it goes by. So instead of pulling on some stars a little bit and other stars a little bit, it pulls on the same part of that other galaxy the entire time. So it can do a lot of damage to the other galaxy, so much so that they don't pass each other, but they come close, and so much energy has gone into the individual galaxies that the orbit shrinks. So instead of whizzing past, they kind of go whoop, and they'll just encounter each other once and basically loop around for a second time and merge. Whereas in a cluster, if you had a galaxy like our own and another spiral galaxy, they're moving so fast that the stars in one galaxy doesn't affect the other, and the two can just pass through each other. But the gas will remain in the middle. Just like in that picture before of the bullet cluster, the two clusters of galaxies, the galaxies themselves pass through each other, but the gas that was in between the galaxies hits and gets stuck in the middle. And we'll see I hope we'll see a picture of that. So this is a picture of one of these compact groups where you can see all of these galaxies. They're about the same distance, and you can see how close they are. You know, they're really close to each other. Not much bigger. The distance in between them isn't much bigger than their size. So here's a simulation of two galaxies merging together. We can see, I guess, the blue represents the gas in the galaxies, and they distort each other dramatically. You'll get some star formation in both of the galaxies. The blue, I guess, is representing the young stars. And then finally, at the final stage, you end up with essentially just an elliptical galaxy, right, over in the final stage. And what's strange about this elliptical galaxy, and you can see it sort of in the picture, is that you have a component of young stars in there on top, because they were just born in the merger, but basically the shape of the galaxy settles down to an elliptical galaxy over the course of about 1 billion years. So it looks like an elliptical galaxy, and your hints that you still see some young stars. So that's the hint that it formed in a merger quite recently. So when we're looking at the Antennae galaxy, we're seeing something in this middle stage where things are still in the process of merging. But then eventually it just settles in to an elliptical galaxy. So if we think about it, if you have lots of collisions, a collision basically will turn, if you take two spiral galaxies and smush them together, you make an elliptical galaxy, if the two spiral galaxies are about the same size. If you take a spiral galaxy and elliptical galaxy and smush them together and they're about the same size, you get an elliptical galaxy. So you can see these mergers tend to make elliptical galaxies from whatever you start with. Right? If you start with two ellipticals, you get an elliptical. You start with two spirals, you get an elliptical. You start with a spiral and elliptical, you get an elliptical, as long as they're about equal size. So if we look in a region of space where you have lots of collisions and lots of galaxies interacting, we end up expecting more elliptical galaxies than spiral galaxies. And that is what we see, right? So this is called the morphology-density relation. As we go to places where the density is higher, the shapes of galaxies change. We go from more spirals in the low-density regions to ellipticals in the high-density regions. Another thing that can happen, so here's a picture of different galaxies, and you can see, lots of things that are merging, right? So all of these pictures show interacting galaxies. And this one isn't that one, I don't think. They don't look the same, but even you have this big one here. Now, another thing that's interesting that can happen, which I don't think I talk about in a slide, is if I have a spiral galaxy and it goes into the middle of a cluster, you remember the cluster is full of gas. And so I can have a spiral galaxy who has lots of gas. It goes into the dense part of the cluster. Let's say it doesn't run into another galaxy. But the gas in that galaxy will interact with the gas of the cluster and effectively just become part of the cluster gas. So this galaxy will flow into the cluster and it will lose all of its gas when it goes into the dense region of a cluster. So you actually, what is that going to do? That's going to turn a spiral galaxy into do you remember that type of galaxy that has a disk but no gas? We call that an S0 galaxy. So that's how an S0 galaxy gets made. It's a spiral galaxy that has gone into the dense regions of a cluster, and essentially all of its gas goes away. So we can actually see that happening. You can ask the question, if I take the gas away from a spiral galaxy, does the spiral structure disappear? And it does, because we do see galaxies where just that has happened. So in the center of these clusters, in this intermediate region, we see lots of S0 galaxies, in fact. I don't know, that might be one, right? That one doesn't look like it has much spiral structure, whereas that one does, and that one does. And as we go into the middle, maybe that's also an S0 galaxy, you see? But a little bit of imagination. So how do galaxies get built, right? So we know that these collisions are very important in how galaxies interact with each other. And so it turns out if we imagine going back in time before all of these collisions have taken place, you would naively say that the galaxies back then would be physically smaller than those today. And indeed they are. So this is a picture on the top of distant galaxies, and we're sort of looking back in time there. We're actually going to do a worksheet about that in a little bit. But the galaxies in the early universe are typically smaller, and with time, a few things can happen, right? So over here we have lots of small guys, and some of them are blue. They still have recent star formation. They've made some green, which means that the star formation is in the past. And as we go forward in time, you can see over here there's fewer galaxies, but they're bigger. And that's because a couple things have happened. Some of these galaxies have merged with each other to make bigger galaxies. And you'd be like, oh, you said when two galaxies merge, they make an elliptical. And that's true, but a spiral can pick up a small galaxy and grow bigger. And that small galaxy will make the spiral bigger, and it will also bring new gas to that spiral galaxy. So if a spiral galaxy picks up a small galaxy, which happens often, it becomes a bigger spiral galaxy rather than an elliptical galaxy. A second thing you'll notice in the picture is that these galaxies here that didn't have ongoing star formation, as we go forward in time, they just get redder and redder. So we have galaxies like this guy who is just getting redder and redder with time, because all that's happening is its stars are getting older and older, and it's not been rejuvenated with another influx of gas to make new stars. Over here we have a funny one, which is like an elliptical galaxy with recent star formation, which is just what we talked about when we have a merger, that we can get more stars to form. So when we look out at distant galaxies, as we'll learn very explicitly, we're going backwards in time, and we can see what the universe looked like in the past. The interactions with other galaxies will cause more stars to form all of a sudden, like in our antenna galaxy. It also can cause matter. When you're slamming all this gas into each other, the gas gets very mixed up, and that can divert material down onto the central black hole. So that will cause two things, and we call these things starburst galaxies, so galaxies which have lots of star formation that we think is due to a merger, but also turning on the active galactic nucleus will happen in association with a merger of galaxies. So what's happening is you can see these two are connected. We're forming a lot of stars, and ultimately, after a merger, we end up with a bigger elliptical galaxy usually, and at the same time, we're also feeding the black hole. So you can see that elliptical part of a galaxy will grow due to mergers, and so will the black hole. So that may be why those two end up growing in proportion to each other, that you have a nice proportionality there. I guess they're out in the hall. That's just weird. But most of these interactions took a while ago, took place when the universe was much younger than today, but it's still going on today. And the reason why it was taking place a while ago is because the universe was smaller a while ago. Everything was packed into a smaller volume, so there's more interactions going on in the past than today. So if we look at a picture here, zoomed in, of really galaxies from a long time ago, we just see these little blobs that are basically the size of the Large Magellanic Cloud, something like a 10th or a 30th of the mass of our big galaxy today. So here's some starburst galaxies, just to give you an idea. So we see they look kind of messy. In both cases, we see lots of signs of interaction. On the left, we actually see two galaxies that are merging together. On the right, we see sort of it looks like an elliptical-shaped galaxy, but it has a lot of dust in it as well, which indicates that it had gas. So it's kind of a weird elliptical galaxy. So these guys were identified by having lots and lots of star formation going on. So we see that the star formation and the interactions are going together. So if we look, we can actually look inside, right? So this is a big galaxy in the center of a cluster, and we call these central elliptical galaxies, we call them CD galaxies. I don't know the history of that, but if you see that anywhere, a CD galaxy is a big elliptical galaxy in the middle of a cluster. Here, if we look at this, what this is showing is a long exposure, and you see it's an elliptical galaxy. If you take a short exposure, what you're going to get is just the very brightest parts of the elliptical galaxy will show up with high contrast. And effectively, if you look in the middle of that elliptical galaxy, you see that it contains several elliptical galaxies within it still. You're like looking into its belly. And those little elliptical galaxies in its middle merged with this big one, and they're not yet fully digested by that elliptical galaxy. And eventually that structure will disappear, but for now we can see it. This is not like a fake. All I've done is the little inset is just a different color stretch than the outer to highlight the brightest part. It's not like I mashed them together. Pretty cool. So here's another example of the same, that we look in the middle, we can see a double AGN in the middle of this interacting galaxy as we zoom in, right? So again, we have something that looks like an elliptical galaxy, maybe quite happy, except we have lots of dust and a double active galactic nucleus, presumably from one of the parent galaxies and from the other in the middle. So basically, to highlight it in a picture, if we take two, what we call a major merger is when we take two galaxies that are about the same size as each other. The result of that is an elliptical galaxy, essentially regardless of what you start with. On the other hand, if we take a spiral galaxy and a small galaxy, a dwarf galaxy, meaning a much smaller galaxy than the spiral, it could be an elliptical, it could be an irregular, it could be another small spiral galaxy. What we get is basically a bigger spiral galaxy. So our galaxy is growing by eating smaller galaxies, so it gets bigger and bigger. Also, we have just gas flowing in from the halo that's feeding the disk of our galaxy, making it bigger and bigger. But eventually, in a few billion years, we're going to go through the top one, and bam, our galaxy is gone. I mean, you know, the stars are still there, but it no longer looks, it goes to its next stage of being. So this just is reviewing what I just said. So if we look on bigger scales, we can ask, well, the galaxies are arranged into these clusters. It turns out that the clusters aren't uniform throughout the universe, and they arrange themselves in bigger structures, which are shown here. And this is a tricky sort of picture. What's plotted, we're sort of plotting how far away something is versus where it is in the sky as I go from right to left. But we can't measure directly how far away it is. We measure the velocity it's moving away from us. So that's a key subtlety. So imagine if we're in a cluster, like this coma cluster here. The galaxies in the coma cluster are moving around each other like this. So if I measure different galaxies in the coma cluster, some are moving towards us faster, and some are moving away from us faster. So the coma cluster is all at, let's say, this distance from us, but all of these galaxies along here are in the coma cluster, but they're not spread out in space. Remember, that direction is velocity. They're spread out in velocity. And we converted velocity into distance using the Hubble law. So this is a weird thing. Like if you look at this picture, you'll notice that like this cluster, this thing seems to point at us, this thing seems to point at us. Here's another cluster, it seems to be pointing at us here. Here's something, it's pointing at us. It's not that they're pointing at us. It's a cluster of galaxies, and the galaxies are moving around like this, randomly, but when we draw a picture like this, it makes it look like they're in a line towards us. Does that make sense? This is called the finger of God effect. Like when we make a plot like this, all these structures seem to point at us. It's just has to do with how we make it. But the other thing that you'll notice is that there's regions where there are very few galaxies, and we call those voids, and that there's large structures that go across the sky, like this one, which are real. They're not due to this effect of things piling up at different velocities. So the universe isn't on this scale now of 100 megaparsecs. Remember, the size of a cluster is about 1 or 2. So you can see this is the width of the cluster is more or less right in this direction, but this direction is expanded by the velocity of the cluster galaxy. So really the cluster is some little ball right here, about as big as what I'm drawing, and then it gets spread out in velocity just due to the gravity that holds the cluster together. So if we were to look at the scale of like a region about 100 megaparsecs, then if we look like a region like this big, it looks remarkably similar to another region. That there'll be structures that are 10 megaparsecs in size, but then when we go to further distances, you can see on average, when we average out over a region that's 100 megaparsecs or larger, things on average look the same in different parts of the universe. So we see these filamentary structure here, like this. We see voids. This is the picture that we were looking at on the last page. It's just this little region. And as we go further and further out, you can see that structure of voids and filaments continues as you go further and further out, but that if you think of a big region like the size of this region, this looks remarkably, on average, similar to this one or that one. It would be hard to tell where you were, okay? But if on a smaller scale, I'm either in a filament or I'm not in a filament. But on a larger scale, one part of the universe looks like another. It's like bubbles, like a foam, right? If you're in a bubble or on the surface of a bubble, that's quite a bit different. But if I'm in this part of the foam or that part of it looks more or less the same, if you know what I mean. As you go further away to the top and the bottom, it's not that there's fewer galaxies. It's just as you look further and further away to get into this picture, you have to be detected. So when you're further away, you're thinking that picture's made with brighter and brighter, inherently brighter galaxies. And you're just running out of bright galaxies that can make it in. Now, if we look very close to us, so within this region here, in 3 dimensions, this is what it looks like. So the local group is here. If we look up in this direction, we have the Virgo cluster, and the Coma cluster is in a similar part of the sky in the same direction. But then there's also other big groupings of galaxies all over the place. And in fact, we're sort of, that's not what I wanted to do. We're in a filament that goes between the Pegasus cluster and across through Virgo and over there. Here's our local group. Okay? So we could try to simulate this and ask, well, how come we have this filamentary structure? And if we go, the basic idea, and we'll learn more about this, is if we go a long time ago and imagine the universe was almost smooth, and you ask what does gravity do to that, the regions that are a little bit more dense, their gravity will overcome their motion and pull them together. And basically this is a numerical simulation of showing if you start with something relatively smooth in the past, it'll evolve forward and form these filaments quite naturally. And on top of just what the dark matter is doing in this, they've tried to figure out how stars are forming and galaxies. And you can see that big clusters of galaxies form at the intersection of these filaments.